People, home stretch. So let's talk about writing quadratic equations given the roots. Now we've actually had some practice with this already. A couple lessons ago, I gave you some problems where you had to do this. And I gave you what I was calling the x-intercepts. So I said, given the x-intercepts for this equation, find a simple quadratic equation that satisfies that given information. And you're essentially doing the same here, except instead of giving you x-intercepts, I'm giving you real roots, which do come out as x-intercepts, but also imaginary roots, all right? And what you might remember, hopefully, is that when a quadratic has imaginary roots or imaginary solutions, it doesn't actually touch the x-axis, right? But when a quadratic has real solutions, for example, 3, -5, and 0, 2, it should be crossing at 2 points. And when a quadratic has just one solution that is real, that's like a touch and turn on the x-axis. So we've basically got discriminant is positive, discriminant is 0, discriminant is negative. And this is basically what your solutions come out to be. 2 real solutions, 2 real solutions, 1 real solution, and imaginary solutions. So now we should be able to write quadratic equations given those solutions, given those roots, for all 3 cases. Okay? So I'm going to do just a few of these examples and then have you try the rest on your own. So for A, given these 2 roots, find a quadratic equation in standard form. Okay, so from here we've talked about what factored form looks like. In factored form, leading coefficient, and then your 2 factors, x minus the first x-intercept, x minus the second x-intercept. All you have to do is plug your x-intercepts in. Y equals a, x minus 3, x minus -5 makes that x plus 5. From here, we have to multiply this out to get to standard form. I'm going to leave that up to you guys to do it and check with the key. But this is your setup, right? That's factored form, take it to standard form. What if you have a repeated root, all right? So instead of 2 real solutions like you have in A and B, what happens when your root repeats, all right? And we know what that looks like. X-intercept and vertex are the same point. 1 real root, 1 x-intercept. Well, it's the same setup. You start with factored form. Except this time, that root shows up twice. Y equals a, x minus -3 makes it a plus 3, and x plus 3 again. Now from there, you can expand that out to create standard form, all right? But this is the kicker, all right? So I want to talk about D. Because we've had practice with doing real solutions before, but what happens when you're given the 2 imaginary solutions, the 2 imaginary roots? How do you come up with a quadratic from that? It's actually a very similar process. So we still start from from vertex form. And notice the 2 roots that have been given to you here. The 1 root that has been given to you is 2 plus 2i. So here's the thing about conjugates. Complex conjugates always come in pairs. So if I tell you that a quadratic has 2 plus 2i as one of its solutions, you can automatically infer that the other imaginary solution is its conjugate, 2 minus 2i. I don't have to tell you that, it's implied, all right? It's something you should remember. So imaginary roots, they always come in pairs, and we're using the rule of complex conjugates. So actually, I do have 2 imaginary roots for this quadratic, and I can do my setup just like this. So I have y equals a, x minus the first x-intercept. I'm sorry, not the x-intercept, because these are imaginary. There are no x-intercepts for this quadratic. The first root. X minus, I'm going to open another set of parentheses to keep the contents of that root contained. So x minus the first root times x minus the second root, 2 minus 2i. Now from here, there are a few different ways that you can solve this. I like to do it the difference of perfect squares way. I'm going to show you what that looks like, but I want you to keep in mind that difference of perfect squares is going to show up at some point within these steps. So from here, I'm going to distribute that negative inside of each factor. This becomes x minus 2 minus 2i, and this becomes x minus if you would like, you can multiply this by this, essentially a trinomial, by setting up a big 3x3 box. And if you'd like, one way to solve this is to do box method to multiply things out. So that is one way to do this. You can do all the distribution, 9 distributions total, using box method to solve that. Or you can notice that actually what you have here is a difference of perfect squares. Let me grab another color and I'll show you what I mean. So my difference of perfect squares, notice the repetition there, x minus 2, x minus 2. I'm actually going to contain those in their own set of parentheses. And 2i, where the signs are different. This is a minus 2i, this is a plus 2i. In other words, you basically have this right now. You have a and a minus plus b and b. A minus b times a plus b. That right there is the factored form of a difference of perfect squares. And so what we can do is essentially identify, okay, well, what are the two squares here? So, carrying down my leading coefficient, this right here, that's our a value. So if I square that, that gives me a squared. I'm going to open a set of brackets here. X minus 2 squared, that's a squared, minus, and then my b value, b squared, 2i squared. I'm going to close the brackets. A squared minus b squared factors into a minus b times a plus b. This right here is a squared minus b squared. That's your difference of perfect squares. So, in order to what are we doing? Oh my god, I just completely lost my train of thought. We're finding the quadratic equation in standard form with the given roots. Cool. Okay. So in order to multiply this out, taking this up here, y equals a, we can do x minus 2 squared, which becomes x squared minus 2x minus 2x plus 4. Minus 2i squared. The square goes on the 2 and the I, so that becomes minus 4i squared. So rather than doing that 9-celled box, I can actually identify the difference of perfect squares here and condense it down to a fewer terms. From here, combine your like terms. X squared minus 4x plus 4. Notice I squared is appearing. That means this is negative 4 times negative 1, so that's a positive 4. Almost done getting this into standard form. X squared minus 4x plus 8. And you have your leading coefficient in front. If you'd like, you can leave that there, or you can multiply it through. So y equals ax squared minus 4ax plus 8a. So that would actually be the general form of a quadratic equation that has these two imaginary roots. If you're asked to find a simple quadratic equation that has those roots, you wouldn't actually have to worry about that a value. And that's your final solution. I'd like for you guys to try B and E on your own. Remember, use the rule of complex conjugates. Do numbers 1 through 7 on lesson 5, and have a great weekend.